All right, let's get started. So today the plan is to see another very important algorithm called Grover's algorithm, which has very important implications in real world cryptography. So Grover's algorithm is an algorithm that solves what is called the unstructured search problem. So let us say that you have a database and you are trying to search for some keyword in that database. So if your database is of size 2 to the n, then in general you expect to take 2 to the n time, right, to look for a particular keyword. And Grover's algorithm allows you to do it in 2 to the n over 2. So it offers a quadratic speed up, right. So this is a very important improvement because it allows us to well, the implications that it has is that this means that the key sizes should be doubled. Like if you can search in a search space, if you can search in square root of the worst case time, right, then this means that if you're searching for a secret key in the key space, right, then this is offering you a square root speed up. So this means that the bit length should be doubled, right. So this is one of the important implications that this algorithm has, and moreover from a theoretical point of view, it's really a very interesting algorithm. So we'll see it today. And we'll see how it connects to the QFT that we were talking about yesterday. So let's get started. So first, of course, we want to define our problem here. Okay, so the problem is, let's cast it in our usual language. So let's say that I have some function f which is going from 0 1 to the n to 0 1. Okay. And for simplicity, I will give you a promise that there exists at most one point x star such that f of x star is equal to 1. So I want to sort of note right off the bat that this is a simplifying assumption that there is only one point that satisfies the function. This restriction could be removed, but we will not look at that. We will look at the algorithm with this simplifying assumption. You will see why. Okay. So good. So basically I have this function, I have one point that satisfies the function and I want to find this point. Okay, so this is my problem. Okay, so you can think of this as a search problem by mapping it to searching a database. You can also think of this as inverting a one-way function. So how is that? Can you try to come up with a way that I can use this problem to represent this inversion of a one-way function? So let me write down a problem prime, which is that if I give you some function g, if I give you this function g and some y, okay, then the question is to find x such that g of x is equal to y. And here again I will make the simplifying assumption that g is injective. So you can see that in fact if I have a way to solve problem, then I can use it to solve problem prime, right. I can just redefine the function so that it solves this problem. Can you tell me how? how should I want to define f such that you know, it captures problem prime. How should I do that? Good. So f, so you know, I define f such that you know, it has g and y hardwired. Okay, and I can say that, you know, f of x is equal to 1 if and only if g of x is equal to y, right. So, this way I can use a method for solving problem to solve problem prime. Okay. So, that's clear. Okay, good. So, now let us see Grover's algorithm to solve this problem. So, we will focus on our first the first representation of the problem. Okay. So, where I have a function f and one satisfying point and I want to find that point. So, let us look at Grover's algorithm. So, first I will remind you of some notation that we have used before. So, if I take a function x to, you know, minus 1 to the fx x, right, I am going to call this, I am going to sort of call this transformation as OF. We have seen this in great detail in the past, right. So, let's not go into that any further, we will just apply this in an abstract way. So, now the first thing that we want to do is we want to prepare our uniform superposition over all inputs, that is what we often do, right. So, prepare psi, which is summation over x 1 over 2 to the n over 2 x. Okay. So, no surprises there. Now, let us repeat the following two steps k times for some k, which we will set later. So, what are the two steps? So, A is that, you know, I apply my function oracle, and B is I apply this map, which I will call reflection about the mean. So, in particular what this map does is that, you know, if I have some summation of summation over x alpha x x, right, it converts this to summation over x to alpha minus alpha x x, where alpha is equal to, or yeah. So, where I define this alpha within these brackets as the mean of all amplitudes. So, I sum all the amplitudes and I divide it by 2 to the n. So, okay, so this step is so far a mysterious step, right. So, this is what I call reflection about the mean map. And this, what it does is that it converts alpha x to this 2 alpha minus alpha x, okay. And once again here alpha within the brackets, maybe I should call it something else instead of alpha, just to avoid confusion. Let me call it mu, okay. Let us call this mu. I hope I remember to stick to that, but at least let us try that. So, mu is the average amplitude, okay, and what I am doing is I am changing alpha x to 2 mu minus alpha x, okay, and then having done this, I'll simply measure all n bits. And the claim is that, you know, with constant probability, I will find the point that I am looking for when I do this measurement. This is the claim. So, this is a strong claim, and actually it needs a very careful proof. So, we will look at the analysis. There are many things to look at. First of all, is the algorithm clear? Are there any questions about the algorithm? I prepare the superposition, and then in a loop I repeat the following. I compute the function and I compute this you know, reflection about the mean. Why is it reflection about the mean? We will see. Okay, but whatever map this is, I am going to compute this and then I will measure. Are there any questions about the algorithm? So, there is at least one serious question that should arise right now in your mind. Okay, I mean, I said I will specify it later, but I am happy to specify it now, something like this. Very good, that is the question I was hoping for. So, how will we generate this map? So, in particular, why is this a legitimate operation to do? Right. So, I need to establish that this is a legitimate unitary operation. So, yes, I will establish that. But exactly, so you have to worry about that, right? And I mean, there are other questions like what does this have to do with QFT, for instance, which we talked about so much last time. Why am I showing this algorithm right after that? And then another more abstract question which at least I like to think about is that, you know, there is this general idea that we have been discussing that, you know, the extra power is this superposition, this quantum Fourier transform. So, how is this making use of that, right? So, it is not clear right now where the quantum Fourier transform is coming in and so on, but we will answer all these questions. Okay. So, first of all, let's analyze this algorithm. So, why should it even work? So, first we will see a geometric view of the algorithm. Okay, this will give us good intuition, but it will turn out that algebraically, you know, to convince ourselves, in fact, you need care and you have to establish several things. But first, let us start with the intuition. So, it has a really cute geometric intuition. Okay, so let us say that you know, I am just mapping the amplitude over all the points. Okay, so in the first step, when I generate the superposition, the amplitude is sort of distributed equally, right? So, on every point in the space, this is my amplitude, and what is this? It is 1 over 2 to the n over 2, right? Does everyone agree? So, this is just from this first step. So, I am preparing psi, which is this, right? So, it is a uniform superposition. So, the amplitude is equally distributed and it is just this. Everyone agrees? Okay, very good. Now, the second step is interesting, right? So, now I am going to apply my, my function oracle. So, now can you tell me what is going to happen to this nice picture that I have? What's going to happen? So, basically x star, right, the amplitude will flip. Why? Because I applied a -1 to the fx, right. So, there is only one point x star at which fx star is actually equal to 1, for the others it is all 0. So, the others will stay at you know, they will they'll stay at the same point, and this one will simply flip, right. So, its amplitude will become negative. Now, note that when I do this, then there will be you know, a little bit of reduction in the mean amplitude, right. So, because I now flipped one, so the mean will come down a little bit, but it is only one point in an exponential number of points. So, you know, it is not very much. So, that is fine. Okay, very good. So, we did this. So, remember that, you know, we were doing these steps in a loop. So, we were going to apply this OF computation, and then we were going to do the this, you know, funny reflection map. So, let us see what happens with this reflection map, right. So apply this reflection map. So remember, what does the reflection map do? So it takes alpha x to 2 mu minus alpha x. Remember, this is what it does, this is what we defined, right? So alpha x goes to 2 mu minus alpha x. So now can you tell me what this picture will now look like? So in particular, let us say that x1 is not x star, okay. So can you tell me how does x1 change? Yeah, so it will remain almost the same, right, because it is already very close to mu, okay. So you know 2 mu minus it will be almost the same. So you know it's almost there, and similarly for all the other points. But now this is the cool thing. So now what happens to this x star? What happens to its amplitude? It becomes greater, right? So now our x star is going to look like this, okay, and the others will sort of stay more or less where they were, right? So we are going to sort of keep doing this. As I already said, we are going to perform this in a loop, right? So at this point, what is the amplitude of x star? So here roughly what is the amplitude of x star? 3 times 3 mu, okay. And then in the next iteration, can you tell me how much does this amplitude grow? 5 mu, right? So in general, after k iterations, the amplitude is of x star is how much? It's something like 2k minus 1 over 2 to the n over 2, okay, because it became 3, 5 and so on. So you can compute that after k iterations is going to be 2k minus 1 over 2 to the n over 2. So now by setting k as 2 to the n over 2, this amplitude becomes constant. So right now we are only looking at the idea of the algorithm. We will do a more careful analysis in a little bit, okay. But the point is that you know, at least intuitively from the geometrical geometric interpretation of the problem, we can see that, you know, essentially we keep doing this, right, and the amplitude of x star alone keeps growing, okay. The others, you know, they decrease very slowly, right, and the hope is that after a sufficient number of iterations, I am going to get something which has constant amplitude. So remember, the denominator is 2 to the n over 2, right. So if the numerator is roughly 2 to the n over 2, then I start getting a constant probability over here. And once I have a constant probability, I can repeat the experiment many times and hope to get a pretty good probability. Okay, so this is going to be the idea. Now there are many things which we have to work out, okay. So we will do a careful analysis. Let me just complete this sort of high level description and then we will go to that. So yes, this amplitude becomes constant, and you know, I can repeat to amplify this probability. Okay, and this means that you know, from the classical 2 to the n, I went to 2 to the n over 2. Okay. But actually here I lied a little bit. So, classical deterministic is 2 to the n, but classical randomized can actually do better. So, does anyone know how much better you can do with randomization? So, there is a very famous birthday algorithm or birthday analysis. So, if I instead of going serially, if I pick points at random, then I can hope to find the probability sooner. So, this is something you can explore in your next homework. For now, I will just tell you that using the birthday algorithm, you can actually get classically 2 to the n over 2. But the nice thing is I can use the same trick with quantum as well. So, birthday plus quantum actually gives 2 to the n by 3. So, there are still a few things to show. I mean, even with this hand wavy geometric view, actually maybe before showing that, it is worthwhile spending a little bit of time. So, if I want order 2 to the n by 3 algorithm, then what I do is the following. So, I make some k queries randomly to f. Okay, I store these in a database. And then define gx equal to 1 if fx is in the database. Okay, and then optimize for k. So, by using this this approach, basically extra randomization, right. So, I make a bunch of random queries and store the results, okay, and then I use that in speeding up my algorithm. When I optimize for k, I get 2 to the n over 3. Okay. So, this is something which I won't spend more time on in class, but you can study this later.